Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. For billions of years, we thought we knew the recipe for a diamond. Immense pressure, searing heat, and geological time measured in eons. Diamonds are Earth's ultimate pressure cooker product, forged hundreds of miles beneath the surface in the mantle. But what if I told you that one of the most unassuming creatures in the deep ocean, a simple stationary filter feeder, might hold the key to synthesizing diamond-like structures at room temperature and ambient pressure? This is the biogenic diamond problem, and the unlikely suspect is the deep-sea sponge. Diamonds are pure carbon atoms arranged in a face-centered cubic lattice, a perfect, incredibly strong structure that defines the hardest known natural material. The problem isn't just making carbon hard, it's forcing the carbon atoms into that exact, hyper-stable crystalline formation without the incredible energy input of a tectonic plate collision. This is where biology enters the chat, specifically the world of siliceous sponges, such as the breathtaking Eupulctella aspergillum, famously known as the Venus flower basket. This sponge lives kilometers deep in the dark abyss, and its beauty lies in its skeleton. The Venus flower basket doesn't make diamond, at least not in the traditional sense. Its intricate skeleton is composed of silica spicules, essentially glass fibers. But the structure of these glass fibers is what has captivated materials scientists. These spicules are not simply disordered glass. They are exquisitely ordered, built in concentric layers around a central filament, forming a near-perfect, optically optimized lattice. This biological architecture results in a natural fiber optic system, perfectly channeling light even at sharp angles, giving the sponge's skeleton a mechanical stability far superior to man-made structures of similar composition. The sponge accomplishes this structural mastery through biological control, utilizing specialized proteins and enzymes to deposit silica precursors in precise geometric arrays, often at incredible speeds, relative to geologic timescales. So, the mystery isn't about silica, but about the asterisk process. If a sponge can biocatalyze the precise formation of a structurally perfect silica lattice, a challenging feat requiring atomic-level control, could the same underlying mechanism be adapted by nature to manipulate carbon precursors? This is the core of the biogenic diamond problem. Scientists theorize that some deep-sea organisms may possess enzymes capable of reducing and stabilizing carbon molecules under specific, low-energy conditions, forcing them into highly ordered, stable configurations. The deep ocean provides the perfect environment for this kind of subtle chemistry. It's cold, stable, and rich in dissolved carbon compounds. Crucially, organisms in this environment, often associated with hydrothermal vents or deep sediment layers, operate under chemical gradients that are fundamentally different from the surface. Some of these hypothesized biogenic carbon lattices might not be the flawless cubic crystals we traditionally call diamonds, but they could be carbines, or highly stable, nano-structured carbon compounds with superior properties, perhaps even hexagonal diamonds, which are predicted to be harder than cubic diamonds. Researchers are focusing intensely on the biological machinery itself. The proteins responsible for the sponge's silica construction are known as silicatines. These enzymes act as molecular builders, directing the deposition of mineralized material. Could there be a hypothetical carbonin, a sister enzyme that guides the precise placement of carbon atoms into a tight, stable array? The implications of solving this problem are staggering. If we can decode nature's method for biogenic lattice synthesis, we could revolutionize material science. Imagine growing super hard, optically perfect materials in a lab beaker, at room temperature, without requiring the gigapascals of pressure currently necessary for artificial diamond production. This technology wouldn't just be about cheaper diamonds. It could lead to self-assembling microelectronics, incredibly tough and light biomimetic armor, or next-generation energy storage devices. The humble deep-sea sponge is reminding us that extreme rigidity and precision don't always require extreme energy. Sometimes, they just require the right enzyme. The Biogenic Diamond Problem highlights how much we still have to learn from the planet's least accessible ecosystems. The ocean floor isn't just a graveyard of failed evolution. It's an active laboratory where life is constantly prototyping materials that challenge our conventional understanding of physics and geology. For more incredible facts like this, don't forget to subscribe and turn on notifications.